Good morning, guys, and welcome back to Christmas session this morning. And we were talking about the LGD models, right? So, if you have a look into this, so if you just try to recollect what we were discussing, we were discussing different ways of identifying, of trying to estimate the loss given default for different products, right? We started talking about, so while we were talking, we started talking about the different approaches that Basel uses for valuing LGD. So the two approaches that we looked into it was the foundation approach. The second that we looked into was the internal rating based approach, right? So over here in the foundation approach, we apply standard supervisory weights, LGD weights, and we find and compute the expected credit loss. On the other hand, also under the foundation approach, there is an alternate approach which we call the haircut approach. So the haircut approach takes into account, uh, so it is kind of adapted from the standardized approach, right? And is more or less applicable for collateralized products. So for unsecured products, it is mostly the a priori approach which is taken. And what you do is you just assign 50% LGD to that, to the unsecured approach, to the unsecured asset under the foundation approach. For standardized collateralized products, we use the haircut approach. Right? And what is that haircut? The haircut, as we saw, was the difference between the market value and the purchase price paid at the beginning of the asset. Now, wherever this difference, so there are the differences at the time of reporting and at the purchase time exists, a haircut is applied. Let's say, for example, for most of the most general cases, if it's a collateralized product, you see that the haircut is applied to the collateral itself, the haircut is applied to the exposure, and the haircut is applied to the foreign currency mismatches, right? So there, so the exposure of the LGD over the loss given default. So the objective over here is to compute the unmitigated exposure, right? And what you have over here is the E star. The E star divided by the EAD is the LGD. The LGD is a fraction or is a portion of the E star. Now over here what we saw was that we looked into the recovery from, so we looked into the different definitions of recovery. Now apart from the foundation approach, what we also saw was that there was another alternate approach. What was that approach? That is the advanced internal rating based approach, which applies the statistical methods for model development. Right? So this is where the role of statistical modeling becomes very important. And when we start talking about statistical modeling, there are some very important basic concepts that we would need to understand. So for the first set of statistical concepts that we would try to understand would be in reference to the loss given default modeling, right? So before we go into this, so basically one very important concept that we need to understand or we need to start from is an understanding of the concept of a distribution. Is to start understanding of the concept of a, a bimodal distribution. Right? So what is exactly the mean, median, and mode of a distribution, and so on. And from there we'll talk about that. So we did talk about this before, that how is it the recovery in the process initiates, right? So how is the recovery estimated? Right? It has an intercept plus recovery characteristic plus sum or obligate characteristics plus macroeconomic variables. So over here we'll also explore the importance of macroeconomic variables in the AIRB LGD modeling, right? So do they enter directly into the model? How do they enter? Right? What are the challenges that you face while developing an LGD model? how is it that they can be overcome, right? So in today's discussion, we will be talking, or our discussion would be more focused on the advanced internal rating based approach. So we did introduce some of the basic definitions under the AIRB approach. We said that LGD was nothing but 1 minus the recovery rates, and it generally has a bimodal distribution. And given that it has a bimodal distribution, it becomes very difficult for us to put in any, to fit in any kind of standard distribution or standard models to this. So because each of the models that we generally develop has certain assumptions, and we need to ensure that those assumptions or those necessary conditions are present in the data at the time that they are being developed, right? Okay. So let's start. Let me just start off with the basic concepts in engineering. So even though I had discussed it in the last class, I'll just reiterate because this is important for us to understand because it is this part that from where the statistical modeling also would initiate. So the first thing that comes out over here is LGD is equal to. So LGD is nothing but 1 minus the recovery rate, right? So whatever cannot be recovered or the percentage of the total exposure which is not recovered is just loss given default. So this is one observation that we have had or this is one definition which we saw in the last class. Right? And the second thing that we talked about is that LGD is a bimodal distribution. Bimodal distribution. Now, given that it is a bimodal distribution, the first question, so there are two questions which come in over here which we need to understand. Number one, we need to understand this concept of bimodal. So, bimodal means a distribution which has two modes. Now, the question that obviously would come out over here is that if I have a distribution with two modes, what is its interpretation? How do I interpret that? Similarly, the next question, another question that also comes out over here is that what is this distribution? What do I mean by this distribution? What is distribution? Right? First of all, we'll just introduce these two concepts. And what is obviously is what is the importance of a mode in explaining the behavior or the shape of a distribution. So over here, so there are these are some of the important things that we will talk about. Just to reiterate, right, even though we have talked about a distribution is nothing but it is the plot of the values of a variable along with its relative frequencies. So it shows, what it typically shows is the likelihood of or the likeliness of the outcomes of outcomes of the values in a variable, right? Let's say my LGD has many values, right? The way I have defined the LGD value over here, the way I have defined the LGD value over here, LGD you will see is belonging to 0 and 1. So LGD has been defined as a fractional value, right? So LGD has been defined over here as a fractional value. Now, because I have defined LGD over here as a fractional value, the question that comes out is that if I need to plot this as a distribution, if I need to plot the distribution of this variable, how would it look like? Now, to each of these outcomes between 0 to 1, right? So, for each of these outcomes between 0 to 1, there would be a probability P associated with them, right? So there would be a, a probability P associated with them which is greater than 0. So this probability P is something like the relative frequency. It is a likelihood that a particular value between 0 and 1 will be chosen, right? So any value, so if I pick out any value, let's say zero point 0.5, so if I want to know what is the probability that I'll have an LGD of zero point 0.5, so there corresponding to that zero point 0.5 there will be a probability. If I say okay, LGD between below this value is right, so below this value is say less than equal to zero point 0.6, is so what is the probability that I have of getting a injury less than equal to zero point 0.6. So that's what we can. So these are the type of questions that we can answer from a distribution. So a distribution is nothing but it's a plot of the values of a variable and their relative chances of occurrence, which is very similar to what we call uh, you know so which is very similar to this concept of probability distributions. Now distributions, now talking about distributions, right? So distributions are of two types. So one of the distribution type is what are observed distribution. So observed distribution is the distribution that you create from your data, right? You look into the data, you look into the values, you look into the relative frequencies, you plot them together, you get your observed distribution. The second distribution that you get is your theoretical distributions. So this theoretical distributions are those distributions which are your fitted distribution. So you want to know, you want to fit a distribution, you want to fit a binomial distribution, you want to fit a normal distribution. So when I say that you are trying to fit a normal distribution to a data, what you are trying to say is you are trying to see whether the distribution the that this variable has, the way the relative frequencies are distributed across the values, is it following, is it something similar to that of a normal distribution or not, right? So the first thing before you talk about any kind of before we move into any kind of statistical understanding or AIR modeling, this is the first part that we need to clear out, right? So the first thing that I'll start off with is the very basic concept of observed distribution. Because when we talk about observed LGD, predicted LGD, what we are essentially talking about is the observed LGD distribution, the predicted LGD distribution. And when I say that there is no significant difference between the observed and the theoretical distribution, what I mean is that the pattern that is being shown by the data is very similar to to some of the to given theoretical distribution, right? So the first part that we start off talking about over here is the concept of an observed distribution. Okay, hello, am I audible? Can you hear me? Hi, Kiran, can you hear me? Okay. Okay. So here is a question to just restate the concept from theoretical distribution. So basically, what we are trying to do here is to try to understand the key differences between theoretical distribution and observed distribution from a conceptual perspective, right? So over here, what I'm saying is that okay, I have these three. So we start understanding this concept of the distribution from the observed distribution. Okay. The first over here is the observed. The question that comes out over here is that how do I create my observed distribution? So before I talk about that, before I talk about how to create the observed distribution, so let us see how our distribution would look like. So now an observed distribution, as I said, is created or is created from the observed behavior of the data. This is created from the data set itself. From the data. So let's just use an example over here. So let's say I have a variable x, and for each of the variable x, there is a frequency of occurrence. But guys, just give me a minute. This time I'll just be back and we'll get something. Just give me a minute. Okay, so as I was saying, so now x has multiple values, right? So let's say x1, x2, like this. It has some finite set of values. Let's say xn. Over here we have some values like f1, f2. I have fn, right? So this is nothing but a simple frequency distribution of a variable, right? So you have the value of a variable x and you have the frequency associated with f. So over here what you have is the outcomes x1, which is, you know, so the outcome x1, which is the corresponding frequency to it is f1, x2 the corresponding frequency is f2, xn the corresponding frequency is fn. So this is how this thing actually occurs. So this is a very simple case of a observed distribution where you have the frequency and the respective outcomes. So now the total number of observations that we have over here is, let's say, capital N. So what is this capital N? This capital N is nothing but the sum of all the frequencies. So I add up all the frequencies and the total value that I get is the sum, right? But this frequency the distribution in this form does not give me too much of an idea about the variable values. So I don't know what is why is it important to have x1, x2, x3 like this in this order, like x1 occurring f1 times, x2 occurring f2 times. I don't have any idea. Now, to have any idea, I should be in a position to compare between the values. So I must know that okay, x1 as a value is more likely to occur than x2. x2 as a value is more likely to occur than x3, and so on, right? So I need to have a relative comparison of all the values, and this is where this the particular role of the relative frequency actually comes in, right? So this is where the concept of relative frequency comes in, and relative frequency is defined as, I have Fi by capital. So this Fi by capital N is nothing but it is the relative frequency distribution of all the values of x. So x1 has a relative frequency of f1 by n. x2 has a relative frequency of f2 by n. Like this. So it shows that relative to the total number of occurrence, how likely is x1 to occur, right? So the relative frequency of x1 will be f1 by n. So like this, you have in by. So now one thing that we can see is that corresponding to each outcome, we can always compute its corresponding chances of occurrence, right? So this is nothing but a probability, and corresponding to the probability, you have the set of the outcomes. Now, if I plot this two together in a graph, what I get is my observed distribution, right? So this relative frequency distribution, this table is called the relative frequency distribution table, right? And now if you plot this graph over here, so over here what I have is 0. So 0 over here is the origin. I have the values over here. So whatever what we write over here is the values. So values, and over here what we have is the relative frequency. What we have is the relative effect. So now, if you look into this, I can have three forms of the distribution. So one of the distribution can look something like this, right? Another distribution and another possibility is you have a distribution like this, right? So there are these two possible distributions which can happen, and the third one added to this is these are the three possible distributions that is possible. So the one in the red and the other in the violet are your skewed distribution. The one in the green is your symmetric distribution, right? Now, depending on the nature of the data, depending on the concentration of the values of the variables, we will classify them as skewed. So within skewed, we can tell them or classify them as positively skewed, negatively skewed, and otherwise there is symmetric, right? So, and most of the assumptions or most of the objective of statistical modeling is to make through necessary transformation, even if you have a skewed distribution, the target is to create out a symmetric distribution. So now, before I move on to talk about the distribution further, so let me first clarify the concept of a skewed distribution and a symmetric distribution. Right? So up to this point, is there any questions? This is a fairly simple stuff, but in case if you have any questions. Okay. So over here, if you have a look into this, so let's first of all see what is a skewed distribution. This is your skewed distribution. And the one over here is a symmetric distribution. Now what creates or what causes a distribution to be skewed? And what causes a distribution to be symmetric? That is simply the question I'm asking you. Right? So what is a skewed distribution? What is a symmetric distribution? So basically, if I'm talking about a symmetric distribution, I'm talking about skewed distribution, what I'm broadly concerned about is the way the values are actually spread across the variable. So depending on the nature, the way the values are spread across, I consider it to be a symmetric or a skewed distribution, which is based on the spread of the values. On the spread. Okay. So over here, what we are looking into is nothing but we look into the spread of the value. So how is it that the values of this variable is spread across? Okay. So over here, when I talk about the spread of the values, what we need to understand is that how is it that these values are spread. So now, if you have a look onto this red graph, right, you will see that majority of the concentration of the values are towards the left side, right? So on the left hand side, the most frequently occurring values are captured, right? So you will see that most of the values are actually concentrated in this on the left hand side, right? And there are a few asymmetric values on the right hand side of the distribution, which creates a long tail towards the right hand side. Similarly, for the violet graph, you will see just the opposite. So for both the red and the violet, what you see is that there is a concentration of the values at one side of the graph, right? So it's not that they are very symmetrically produced, right? So the concentration of the majority of the value lies on one side of the graph. On the other hand side, or on the other side, like in this violet graph, you would see that majority of the values lie towards the right hand side of this graph, right? So when I have a look into this, so you will see that asymmetric distributions are created by pocket-wise concentration of values. Because the values are concentrated pocket-wise across, what will happen is that some areas where these pockets fall in, right, will give you a better picture, whereas or will give you more data points, whereas where you don't land up on these pockets, you get a relatively lower level of information, right? So let's say mostly what is the type of what are those cases where I get to see uh, a distribution, right skewed distribution. So most of the cases, a typical example is a loss distribution function of the bank, right? So in a loss distribution function of a bank, what you see is that it's a right skewed distribution. There is the lower losses, right? The lower volumes of losses are more likely to occur compared to the higher values of losses. The reason is that the small value of losses can occur here and there, but that is not a major issue for the bank because the bank is already predicting them and is keeping aside CA's impairment. On the other hand, the challenges occur if the losses which are about to or which arise for the bank is at the tail end of the bank, right? So which is at the tail end. So higher the exposure value, lower is the frequency of that to occur, right? So the entire intuition behind the loss distribution is that the hello, yeah. So the main problem with the bank is that the lower volume of losses are more likely to occur than the higher volume of losses. So the typical loss distribution for the bank would look something like this. So if you have a look into this, you'll see that the majority of the losses or the loss distribution peaks up. So over here, where I've circled it using the red, right? So that is the part where the greatest or the the most frequent losses occur. So what you can see is that the loss amount or the exposure amount over here is very less, right? So it's among the, so if I look into the exposures, so the tail end or the smaller end exposures have higher proportion of losses occurring from there, right? But the losses are relatively smaller. On the other hand, if you look towards the tail ends, you see that the probability of these losses to occur is very low, but the exposure is very huge. So what it says clearly is that losses which have higher exposures, right, are those losses which occur very rarely, because if these losses were to occur, then the bank would end up getting bankrupt. It is to face these losses that you have your very stringent capital adequacy norms and your CRD fast and stuff like that. So this is something that we need to understand over here, right? So a right skewed distribution. So this is a right skewed distribution. Why? Because majority of the concentration is on the left hand side, and some of the value is creating that asymmetry, those outlier or those extreme values lie towards the right hand side of the distribution. Hence, this is called a right skewed distribution. This kind of a distribution is called the right. This is the right skewed. Now, in risk, in credit risk, most of the distributions that we will, uh, so most of the distributions that we generally use in credit risk would be right skewed in nature. The reason being that you know in risk, because it's so predictive, it's so managed, right? So most of the loss figures that we would see occurring would be small, would be of relatively smaller exposures, whereas the larger exposures would have very less chances of occurring. But if they do occur, then they can send the entire bank to oblivion. So so that's the reason why these distributions, this the right skew distribution, especially is very important for risk models, right? Also, what you would see is that in risk, right? So very high income borrowers, very low income borrowers are extremes, right? So let's say you look at the income distribution of a bank's portfolio, right? So what type of borrowers are booked? So basically, you will get to see an average income, right? And then you will get to see tail end values. So again, there would be some right skewed distribution, right? Now, on the other hand, there can be some cases, where you end up having a less skewed distribution as well. So, what are those cases? Let's say it's a very high value card, credit card that you are booking, right? Now, it is given based on your income. But now, what happens is that that, that there is some specific overrides which are done. Now, when an override is done, then you may see that very low income borrowers are also given this loan, given the fact that they have some huge amount of wealth kept with the bank which they had inherited and so on. So, under such cases, you can have right skewed distribution as well. The reason being that if I'm choosing the right skewed distribution, right, if I'm choosing a left skewed distribution, what I'm trying to say is that the lower value, the lower tail values are less likely to occur, and the majority concentration is towards the higher end values. So, so the skewness in a distribution arises because of heterogeneity, right? And this heterogeneity is ample in a credit card or in a credit risk data, because in a credit risk data there are multiple types of borrowers, people from multiple people from multiple professional backgrounds, people from multiple socio-economic backgrounds, and they are segregated across by categorical variables, by across categories. So what happens over here is that you know, so what goes to happen over here is the following: that more the number of categorical variables are there, so the more number of categorical variables are there in the data set, the more heterogeneous will be the data. And the more heterogeneous the data will be, the more uh, skewed will be the distribution, right? So this is something that we need to understand. However, our key objective always remains to ensure that the distributions that we are working with become symmetric in nature. So we want to make this distribution, or we want to make we will always want our distribution to be symmetric in nature, right? So this is something that we would be working towards next, and that's where the role of transformations come in. But mostly, if you take up a variable in risk, credit risk, any credit risk variable, and you try to plot a distribution from there, 99% of the cases it's going to be a skewed distribution, because of the existence of so much of heterogeneity in a given portfolio. All the portfolio variables are not homogeneous in nature, right? So there are some variables again which you get to see very symmetric in nature. Let's say balance receivables or number of accounts which are booked in the books of a bank over a period of time. Now these things they do not change very abruptly, right? So more or less in the long run the values are more or less symmetrically distributed, right? So so depending on the nature of the variable, depending on the scenarios, you can come across any one of these three distributions, right? But when we look into uh, but most of the distributions, be it for the dependent or the independent variables, right, you will get to see that yes, it's mostly it's mostly asymmetric in nature. Okay. So Kiran has a question over here. I'll take it up and then I'll move to the next part. Okay. So Kiran has a question that only the dependent variable needs to be transformed or the independent variables as well. So it depends, Kiran. So mostly, for initially finalizing the approach, starting on with the approach, right? What we do is we start with the transformation of the dependent variable. Now, as we move forward and we start developing models, right? You may see that some transformation of a raw variable gives you a better idea. So we use that transformation as a value. So, so, then that independent variable is transformed, and when you put in the transformed value, what is the kind of results that are coming out, that is checked, and then you decide whether at all to put any transformation for the independent variables or not. So this is something which is specifically decided, right? But just to zero down on the approach, on the modeling approach, on the mathematical approach, what we do generally is we decide on whether to do that. What we generally do is we kind of to decide on the final modeling method, what we do is we first look at the transformation of dependent variable, because for choosing your modeling approach, the distribution that you have for your modeling variable is very 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 important. The dependent variables distribution becomes very important. Okay. So Kiran has a question on it. Does segmenting independent variables into buckets instead of transforming would help? Now, if you are segmenting them into buckets, that is, you are categorizing them, right? So you are converting them, you try to convert them into categories. So that itself is a transformation exercise. Now, if you try to create segments, then that's a separate story. So segmentation is not, so even if you create segments, so you are creating two separate groups of accounts, right? So two separate groups of accounts which are different in terms of their risk levels. So, so segmentation would help you just identify two different risk segments which are different in terms of the bad rates or which are different in terms of certain customer profiling variables. But when you are developing a model for each of these two segments, that is where you would not be able to, so that's where you would be a bit, uh, so, so that's where you would need to understand that whether transformation of the independent variables would be required or not. So, variable independent transformation of independent variables is relevant for model development exercises. Segmentation enables you to segregate heterogeneous groups of borrowers, right? So, so these are the three, different uh, types of variable, types of distributions that we generally have. Now let's talk about the LGD distribution. Okay, so I talked about the two skewed distribution. I'll just talk about the symmetric distribution once, and then we'll move on. So for a normal distribution, for a symmetric distribution, you will see that if you split this data set, right? If you split the distribution, you will get two equal parts, right? Now, when you have these two equal parts, what does it stand for? So, what it clearly tells you over here is the following: that this data contains of this variable contains of values which are not concentrated at one end and which do not have some extreme values lying at the other end. So it is two very different kind of distribution over here, right? So the values that you have on this side of the distribution is very similar to the values that you have at this side of the distribution. So, what is the basic difference between a symmetric and an asymmetric distribution in terms of the nature of the data set? So, for a symmetric distribution, a data set, so the variable that you have is a homogeneous variable, right? So, the values of the variable are more or less homogeneous and there is no presence of extreme values. On the other hand, for asymmetric data set, what you have is a asymmetric distribution, right? So whenever you plot a distribution and you get some kind of asymmetricity, you know that there is an element of heterogeneity. So and the and in such a case, and when you have an element of heterogeneity in your data, then it is not directly possible for you to use only one single modeling method or one single sampling method and get it sorted. Right? So this is something that we need to take care of. Okay. Now coming back to the question, so these are the three types of observed distributions that we generally have, right? Three broad types. Now, now let's try to understand the how would the observed distribution for LGD variables look like. Now, mostly the LGD distribution has so LGD distribution is a bimodal distribution. So the question that comes out is what is the mode? What is the mode of a distribution? Now we know that to characterize a distribution, there are three broad measures of central tendency that we use, right? So one of them is a mean. Okay. So the mean of a distribution is the average value of a distribution. The median of a distribution is the middlemost value of a distribution, and mode of a distribution is the very value which has the highest frequency of occurrence, right? Now, if you want, now by comparing the value of the mean, median, and the mode, you can identify whether a distribution is a skewed distribution or a symmetric distribution. If it is a skewed distribution, what is the type of the skewness? Is it a positive skewed distribution or is it a negative skewed distribution? So by comparing these three figures, we can check that, right? So let's say the distribution, one of the distribution looks like this. So this is a right skewed distribution, right? So what is the mean mode of the distribution? This is the mode of the distribution. Agreed? Because this is where the distribution peaks up. So the point where the distribution peaks up is your mode. Now, the median of the distribution will be the midpoint of the straight line because it's a continuous distribution depending on 0 to infinity. So the midpoint over here of this line becomes your median. And where is the mean of your distribution? The mean of your distribution is slightly biased towards the right, and it has the value over here. So this is the part where you have your mean. Now, why is the mean towards this side? Because we know that a mean, when you're defining the mean is nothing but the average. So it's a sum of the values divided by the total number of observations. Now, given this characteristic, what needs to happen is that there is an average. So when I'm averaging it out, the mean value will tend to get pulled up by the extreme values. It is because of the fact that there are some extreme values lying at this scale end, the mean value is slightly biased towards the upper side. And hence, for this kind of a distribution, the mean is greater than mean is strictly greater than the median, and the median is greater than or equal to the mode. So if a distribution is a right skewed distribution, then the mean should be greater than the median, and the median should be greater than the mode. Right? The relationship just reverses in case of just it reverses in case of a left skewed distribution. Right? So similarly, for a symmetric distribution where mean equals to median equal to the mode. But one important characteristic of this part, it's one important characteristic of this part is that you have a unimodal distribution. So your mode is you just have one single mode in the distribution. Now, one typical case. Okay, so so one of the most important characteristics of the distribution of the LGD model is that it is not a unimodal distribution. It is a bimodal distribution. Now, how do I define this bimodal distribution over here? So, bimodal distribution is a distribution where you have two separate modes, right? So, so there are two parts to it. Right? The first question that comes out over here is that why is it so? The first thing is why do I consider it to be bimodal, right? And how does the bimodal distribution look? This is your LGD, and this is your question, right? So over here, you'll get to see something like this. So one of the modes that happen over here is at zero. So at zero, you see a high frequency of value happens, and it is less than this. So over here you can see that LGD model or LGD distribution has two modes. One, so mode, this is your mode one, and this is your mode. Okay. So the question that comes out over here is that why is it that these two values are so different? So why is it that this distribution is bimodal in nature? The reason is that when either your asset is unsecured or secured, right? So now if it's an unsecured asset and there is a defaulter, it is very difficult to recover assets from him, right? And hence the LGD is nearing to one. Let's say a leasing portfolio, right? An aircraft leasing portfolio. So the person who has taken the plane, right, the aircraft, right, and fails to default, and he defaults on his payments, right. Now, now all you can recover from him is the aircraft machine, nothing else. You cannot just recover anything from him because, and in such cases, the LGD is zero because, or let's take a case where there's a aircraft lease which has been given, right, and then the aircraft crashes, your LGD is one. So basically, in such a case, you cannot do anything about it. So it's mostly seen that LGD distribution is either concentrated at zero or one. So, or if you have uh, a certain distribution, right? So it's concentrated. So both of the recoveries are concentrated at zero. So hardly any part has been recovered, or mostly fully has been recovered. Intermediate values are very low frequencies, right? Now in this case, it is not possible for me to develop any model using this distribution, and hence we need to have a transformation. And to do the transformation, we need to have an understanding of the concept of theoretical distribution, right? So this is the next part of our discussion, which is the theoretical distributions, right? So this theoretical distribution is something which we will do in the Wednesday's session, right? So the next basic objective is to understand theoretical distribution and to see how is it that this LGD can be transferred or can be kind of transformed into a continuous or into a smoother distribution, right? What are the ways of doing that? How can we go about doing this? So this is something that we need to look into, right? And why we do that? After doing this, after doing the transformation, what are the modeling methods that we can use to model LGD? So once we have the framework of the model, so once we have the framework of those models, then we can say that then we can use the data and we can see which is the better model. So now before I close off, I'll just again explain the fact that why we need the transformation. Because when you are developing a model, right, you cannot develop a model on a very abrupt distribution. So the distribution must have a pattern, it must have some kind of a symmetry. So either you need to have a typical symmetry or you need to have a typical asymmetry. Developing models on bimodal distribution is not possible, right? Because we have a bimodal distribution, right? It becomes difficult for us to make predictions because you have one at zero, the other at one. So basically, what you need to do is you need to smooth out this irregularity in the distribution. So before we develop models, there are certain assumptions on the distribution of the dependent variable, right? And in one such assumption is that the distributions have to definitely has to be smooth distributions. So you can be an asymmetric distribution, but you need to have only one mode. Developing models on bimodal distribution is a bit of a challenge, right? So it becomes very complicated. In order to reduce the complications, the dependent variable is so transformed that it becomes one single smooth distribution, right? Okay. So there's a question over here that are we able to convert back the transform values to real values? Yes, we can always do that. There is always a connection function, but we really need not do that because be it LGD or be it they are ordinal values, right? You need so it just gives you an idea of the percentage of the PAD which is kind of not being recovered, right? So you don't really need the actual values because you just need to have an idea about the percentages, and the overall percentage figures are not impacted by the transformation. So that has to be taken into account, right? Okay, so let's take a pause here for the day, and let's continue with the discussion tomorrow. Sorry, not tomorrow, on Wednesday. Thank you.